If you haven't done so yet, make sure that you pause the video and reread the problem before listening on. We basically have ourselves a simple pendulum consisting of this small mass that's been displaced a little bit from that dashed vertical line. And we know that when we release the ball, it's going to oscillate back and forth in a periodic fashion. And the period of that oscillation is governed by this equation. This is an equation you learned in an earlier chapter for simple pendulums. And in order for us to calculate the period, we can see that we need two pieces of information. We need first the length of the string, which is pretty easy because they gave us the length directly in the question. That's just half of a meter. But we also need the value of g. Now, ordinarily, g would simply be 9.8 meters per second squared. But in this question, we're going to have a different value of g, and that is based on the forces that are acting on the ball. So consider the ball for just a moment here, and of course we know that there is a downward acting gravitational force, and that would be mg. But because this ball is charged and it's placed in the presence of a downward directed electric field, there's going to be an additional force acting downward on the ball. So it's not just the mg force anymore, but there's an additional electric force. And that again is pressing down on the ball. And we're going to label that force acting down as the electric force. And in this chapter, we have learned that that electric force is equivalent in magnitude to the magnitude of charge multiplied by the magnitude of the electric field. So in essence, we have two downward forces rather than just the single downward force of gravity acting on the ball. And that's going to affect the value of g. Since we have two forces pulling down on the ball, that's going to increase the effective value of g. And that's what we're going to need to calculate, is that effective value of the gravitational acceleration. And again, it's going to be larger than 9.8 because we have two forces acting downward on the ball rather than just one force acting on the ball. So for the downward force, which we might just call F sub d for downward force, that is going to equal mg plus the value of QE. Now, we were given the mass of the ball. We know g is 9.8. We know the charge as well as the electric field. We just have to make sure that we convert those values into their standard value or their standard unit. So for example, the mass is given as grams, but we're going to have to change that into kilograms by taking the 1 gram and multiplying that by 10 to the minus 3, and that will flip the mass into kilograms. In addition, the charge Q is given in microcoulombs, so we're going to have to change that by doing 2 times 10 to the minus 6th coulombs. Now with those conversions in place, let's go ahead and plug in to calculate the total downward force acting on this small mass. And when we do that and simplify it on our calculator, we're going to get a downward acting force of 0.2098 newtons. That's the total amount of force that's pulling down on the ball. And with that total downward force, we can calculate the effective value of g. We know that the force of gravity would equal the mass of the ball multiplied by g. Now, the force of gravity in this case is supplied by that total downward force. That's kind of the key to part A of this question, is to envision those two downward acting forces as the total force of gravity. It's actually made up of the gravitational force and the electric force, but we're going to treat that as an overall downward pull of gravity. So we're going to substitute in our downward force for that force of gravity, and then if we divide both sides by the mass, we can see that the effective value of g is given by this expression here. So we're going to go ahead and plug in that total downward force that we just calculated along with the mass of the ball. And when we simplify that, we can see that the effective value g is approximately 210 meters per second squared. Now that's much larger than the standard value of 9.8, and that's again because we have that additional downward force, that electric force pulling down on the ball, which is increasing the value of the gravitational force, or perhaps the effective gravitational force, which in turn increases the value of g. And now that we have the effective value of g, we can use the period equation to calculate the period of this pendulum. Let's recall that the length of the pendulum was half of a meter. It's right there. So we'll plug in that length along with our effective value of g. And when we simplify that, we can see the period is approximately 0.307 seconds. This will be the correct answer to the question for part A. In part B, it says that's part A. B says, should gravity be included in the calculation for part A? Well, Perhaps to answer that question, we can recalculate the period, but let's exclude the gravitational force and just sort of see what happens. So we're going to repeat the calculation, but we're going to take out the mg force. So if we did that and we looked at our total downward force, we would knock this term out of the equation, which in turn knocks that out. So we're going to recalculate the FD. And when we do that, we can see that the total FD is going to be 0.2 newtons. So now we just kind of go down to where we were here. Our total downward force is 0.2 newtons. So when we go to calculate gravity, we would change this value right here to 0.2 newtons. So let's calculate or recalculate the effective value of G. And when we do that, we would get G is equal to 200 meters per second squared. And then we come down and recalculate the period by replacing our effective value of G with 200. And when we do that, the new period would become 0.314 approximately. So this is 0.314 seconds. And the question is that significant? And it looks like it is. We can find a percent difference perhaps to see how significant it is. So we'll do a quick percent difference calculation. We'll take the new period, subtract the original period, and then divide that by the original period, multiply it by 100. And when we do that, we see the percent difference is approximately 2.3%. So that would be considered fairly significant if you have a 2.3% difference in your period. That indeed would be significant. So we could say that the answer is yes for part B, which again asked us, should gravity be included? The answer is yes, because if we don't include gravity, then we get a 2.3% difference in the period.